In this video, we discuss vector valued functions, specifically how derivatives relate to vector valued functions, what that tells you about the function. We can use component forms to describe the function relationship by saying what the x component is, by defining a function for the x component and for the y component. Once we have those two different functions, it says what the x coordinate is doing, what the y coordinate is doing. We plug in, say, a value like this number into our function, and we plug into your function, we get out this vector over here. As you change your real number inputs to different real numbers, you get different vectors pointing out into your xy plane. This also works for three-dimensional space. What we are interested in is the curve the vector valued function traces out. So if I click on this arrow, you can see as time evolves, the vector valued function is tracing out this particular curve, which I've called C. The curve itself is called a vector valued parameterized curve. You can think of the vector valued function as describing where a particle is at any moment in time as time evolves, and the curve is the path that particle transverses over time. We've described that if you've got a vector valued function, you can certainly subtract vectors, and because the input is just a time parameter, just like a real number, you can find the distance between these two vectors, this one at delta t away from wherever you're evaluating at, and divide it by delta t. This is just the difference quotient formula, and if you take the limit, what we get is the definition of derivatives except for vector valued function. We just do this component-wise because that's how we handle limits with vector valued functions anyways. And so that just means if you want to take the derivative of a vector valued function, you're just taking the derivative of each of the components. In 2 dimensions, that's the x and y components. In 3 dimensions, that's the x, y, z component. If you happen to have an endpoint, like you're defining your vector valued function over an interval from a to b, you can define what the derivative should be as you hit the end point of A, the beginning point of A, or the ending point of B by taking the appropriate right-handed limit or left-handed limit for each side. In this graph, we can see the vector valued function right here at some time parameter t. We can find a vector valued function that has been displaced by just a little bit. So some that time parameter t plus, in this case, 1. I can make it a little bit smaller, a little bit closer. If I take the difference of the two and divide it by my delta t, or in this case my h, which is 0.7, I get the vector that we're calculating as the difference quotient. It's an approximation of what we think might be the derivative. If I continue taking the limit as my delta t goes to 0, or in this case as h gets really, really small, notice that I get a blue vector. Whoops, well, divide by 0 is the problem, so I can't quite divide by 0. But I get a blue vector that almost looks like it's tangential to the curve. I can use the same sort of difference quotient limit approach to figure out what the tangential vector might be at the endpoints of the curves. If I'm doing at the endpoint of the interval, my time interval is 5, so that's what this point of the curve here is, then I want to use my h's to be negative, so I'm coming at it from behind and keep moving closer and closer when I do this difference quotient to get that tangent vector. And if I'm using the other endpoint, the initial -5 for my time parameter, my interval where I can evaluate my t's, then I want to use positive displacement, or delta t, so I end up getting closer and closer to 0 to get its approximation of the tangent curve. The moral of the story is we can compute these derivatives of our vector valued function, and what it tells us about the curve itself is what is the tangent vector of the curve. So you'll find out that some of the information about the tangent vector is how fast your parameterization is changing, how fast the particle is moving along the curve, and some of the tangent vector information is just what is the curve doing, where is it bending, how much is it bending, is it staying in the same direction. In any case, for computing the derivative of a vector valued function is pretty straightforward, and you should remember what it tells you is the tangent vector for the vector valued function. So it turns out if you're just trying to find the tangent vector or take the derivative of the vector valued function, the theorem says you just have to take the derivative of each of the components, whether it happens to be inside a plane or inside 3 space. It's just each component, which is the normal thing you know how to do. Let's work on some examples here. If we want to take the derivative of, say, a, we apply the same derivative rules except individually to each component as if you're doing it for 2 different functions. The first component is just using the product rule, which is what I have written over here. Now I move on to the second component where I just use the power rule. And as you can guess, if I want to take the derivative of a vector valued function inside 3 space, I just take the regular derivative of each component independently as if they were 3 different functions. So I use chain rule or power rules as needed. Notice that I had a typo for this one, so that's why I changed it for the last component. Okay, this last example is just to reinforce the idea of what you're getting is a tangent vector for the vector valued function at the point you're evaluating at. What that means in this case is that it's asking you to find the tangent vector valued function and then evaluate it at t equals 1, so find out what that tangent vector actually is at time 1, and then try to graph it, either on paper or on a calculator or in GeoGebra. I'm going to show you how to do it in GeoGebra, and in any case, it basically starts with paperwork anyways. First, you have to find the derivative. I want to find the initial vector. I want to find the terminal point of the vector when t equals 1. And I want to find the coordinates of the tangent vector or the derivative of a vector valued function when the time parameter equals 1. Once I have that information, I want to work on graphing it. The way I do it is I first write out 3 different functions, one for each of the components. You could check to make sure these are the right functions I have for my components. Then I like to express my vector valued function by saying r of t equals, and this is where I put a parentheses for my coordinates. My x coordinate is the f of t, my y coordinate is the g of t, and my z coordinate is my h of t. GeoGebra understands what I'm trying to do here, and I'm going to press enter. My particular problem didn't tell me the interval for which my curve is defined, and I don't like these other colored curves from the coordinate equation, so I'm going to click on the colors to get rid of them so I don't have to look at them. Look around, you can see what the shape of that 3-dimensional curve is, and if I want to know what the vector valued function is, vector value output of this function is when t equals 1, I could just plug it into GeoGebra in the following way. R of 1. Press enter, and it gives me the point on the curve that corresponds to r of 1. If I want to see what that looks like as a vector, because it's a vector valued function, I'd write the word vector parentheses. I already did r of 1 in here, so it's equal to a now, so I could use a. But if I didn't do that step, I would still write r of 1 inside there. So I'm going to press a. Now it shows me the vector that the vector valued function is giving when I plug in 1, and it points to the coordinate of that point over there. I could take the derivatives I have on paper to come up with my derivative of the vector valued function as its own curve. I maybe want to call that r prime rp of t. I want to say that is equal to the derivatives I actually computed. So that is a 3t squared. I have to press the down arrow so it doesn't stay in the power, comma 2 times the cosine of 2t, comma negative 2 sine of t squared. I get a second curve. This second curve is the traced out path for my derivative of the vector valued function. It actually is not something I'm terribly concerned about. I don't really care about the shape of that particular curve, so I'm going to get rid of it by clicking on this dot. It still exists inside GeoGebra, but it is not a curve I need to see. What I do want to see is the vector value for the derivative of the vector valued function when t equals 1. So I do the same thing. I write the word vector because I want GeoGebra to graph a vector. I want to put my derivative of vector valued function, which I called rp in this case, at time equals 1. So I put a 1 in here, and there we go. Notice that this vector value function doesn't look like it's on the curve, so it's hard to say that it's a tangent. But that's because our standard form of representing vectors in standard form always have their initial point on the origin. But you can pick up and move a vector without actually changing the vector value so that the initial point is on the curve, so you can see that it looks like a tangent. You could do that in GeoGebra by using the vector function over here and saying the initial point is when the vector valued function equals 1. So that's where I'm going to start drawing my vector for my tangent vector, comma, so now I need the terminal point. The terminal point is the displacement from the initial point, so that the x coordinate is displaced by, in this case, a +3. The y coordinate is displaced by a negative 0.83, and the z coordinate is displaced by a positive 1.69. What I'm doing here is I'm just adding the x component, y component, and z component to the original vector right over here, the terminal point over here. I'm shifting the location of this point so that its new terminal point is the sum combination of these two. I forced that in GeoGebra. I forced GeoGebra to do it for me by creating the coordinates of point with a parentheses. So this should be a 3-tuple because it's giving me a point in 3 space. That point in 3 space comes from the x coordinate. The x coordinate for that point in 3 space comes from my x coordinate of my vector value function when time equals 1, displaced by, I need to make sure I find the right parentheses. It looks like 2 parentheses. Okay. Displaced by the x coordinate of the derivative. The y coordinate for that point will be the y coordinate of my vector valued function evaluated at 1, displaced by the y coordinate of the derivative. And the z coordinate is going to be the z coordinate of my vector valued function evaluated at 1, displaced by the z coordinate of the derivative. I get an exclamation point, which means I made an error somewhere. It's probably parentheses error, and you could probably see where it is. I see where it is now. Z coordinate of the derivative. Okay. I can see that these two vectors look like they're parallel to each other, these two tangent vectors, and it does look like that tangent vector that has the initial point at A is actually tangent to the curve at that particular point. Voila, that is what I'm looking for.